Hello everyone. Today I'll be talking about DreamFusion, RealFusion, and the GitHub repository named Stable DreamFusion, along with some of the code that I've written based on Stable DreamFusion. So let's start. I will start with my main.py, where I give a prompt, set the number of inference steps, set guidance scale, optimize, and then save the image. However, I will go in order and explain what these variables mean. So this number of inference steps, as you know, we start from randomly sampled Gaussian noise at each inference step, and an architecture like UNet or any network that is able to do text to image translation tries to predict the change in the amount of noise through consecutive steps. So that's what number of inference steps, like what happens within a inference step, and I repeat it 1,000 times. So here I have this guidance scale, which I set at 100. What this guidance scale is that on line 149, 143, where guidance scale is basically, a hyperparameter for the difference between the previous noise and predicted noise. So I multiply it with, this difference here. And basically, after the optimization happens, I just save all these images, and there's an optimization process that takes place here, and we're not optimizing this model, but the pred RGB. So I'm not like training a model, but a machine learning model, but I'm optimizing the 3D shape. That's what I'm referring to by model. So stable diffusion is a latent diffusion model, and the aim is to make the computational burden less, right? So we use, variational encoders, and these variational encoders try to do optimization in latent space, right? So that's where I create the latents, for instance, and that's where, this optimization inside the latents happen. We like doing optimization in latent space because it's more, it's less computationally expensive than doing optimization on image space. So image space versus latent space are two important terms. Doing optimization on latent space is just better compared to doing optimizations in the image space because it's less computationally expensive. So we use a 2D unit for this optimization. And, one of the first questions that I asked myself while I was learning this was, why do we use a 3D unit? Why don't we use a 3D unit, but a 2D unit instead? Because, in the code, this is a 2D unit, right? So, and the reason why is that we have the reason for having a 2D unit there is that we are using stable diffusion, and stable diffusion uses a 2D unit. Where we get to 3D is, where we combine this with the nerf, and we sort of try to learn the MLPs of the nerf. So that's where the trick comes in. So we don't necessarily generate a 3D shape right here, but we contribute to the nerf which learns that 3D shape. Then we calculate, the predicted noise. Then we calculate the predicted noise, and take L1 or L2 norm of the difference between the predicted noise and real noise. This is on line 148 here, and we later save the output on diffusion STS example, basically here. And that's mostly it. Like I start out with this icosphere, and I sort of try to improve it, optimize it using this pipeline. So let me pull up the this stable DreamFusion GitHub repository. Some background information. So they call it stable DreamFusion because they use stable diffusion instead of Imagine. Inside the paper DreamFusion, Google used Imagine. But because that model is not open source, the contributors of this repository are using stable DreamFusion. So yeah, another point that I have is, this paper named DibR. This paper called DibR takes a 3D object and takes 100 different poses of that object, and asks the question of how would I 3D reconstruct this object based on 100 pictures. DeepR and DreamFusion differs like a lot because instead of learning the 3D model, DreamFusion is trying to learn the nerf that models that 3D shape. So what I mean by is, the MLPs of the nerf that models that 3D shape. So I think we can now move on to the paper. I will explain the pipeline. Cool. So here we have, the prompt, a DSLR photo of a peacock and a surfboard. Here inside this nerf, we have two MLPs. These might be two MLPs or one MLP. That's an implementation detail. I won't dive into that. But what's interesting is that, with regular digital images or videos, there's like a discrete grid, 256 by 256 grid, let's say, okay? And, all the video plays in that grid, all the 2D images that we open exist in that grid. And the resolution of this grid can change, right? So given that we have a 256 by 256 image, we can increase its resolution to 512 to 512 using super resolution, right? So I cannot do this task solely depending on this 2D grid, this discrete information that exists on that 256 by 256 grid. So I need a function where I give an input and it takes me to some other dimension, right? Other dimension inside that 512 and by 512 grid, right? So I need a continuous function to tackle this task in the problem of super resolution. Here, we have a nerf, okay, and that nerf is, and I give nerf a theta, which is the angle that I look that 3D shape from. And when I look at it from this angle, I see a 2D image that looks, let's say, like this, okay? And if I look at it from the top, I see this. So what this nerf is doing is that it takes in theta as input, and it maps a 2D image that is associated to that theta. So it's a function of theta, right? So this means that I can model this shape as an MLP. If I can learn this MLP using backpropagation, right, I can generate a 3D shape. So that's the whole point of DreamFusion. That's their main contribution. That's the thing that they've released in this paper. So yeah, let's talk a little bit more about the pipeline and how it all works. Let's say that I looked at this 3D shape from 100 different angles. Let's say that I added some noise on top of every 2D image that I have extracted from those 100 different poses and worked with that, okay? So I look at this render, a 3D shape, and I take 100 pictures of it from different poses, and I basically, add a little bit of noise on it. And, usually noise is directly given to a unit, right? In diffusion models, most of them start from, pure noise, and they produce some 2D output. Here, we're adding noise on top of that 2D render. We do that so that we can have some information about the viewing angle. We do not want the unit to learn a 2D shape. We would like the unit to have some knowledge about the weaving angle. That is why noise is combined with that rendering, like the rendered output. This is logical because think of it like how consistent would the model be? Would the 3D model be if it only know about a 2D 2D image, right? So we also have to somehow feed in that data and associate that 2D image with that data. So inside stable DreamFusion, we have a train loader inside the code. Let me move on to there. But before that, I will just quickly go over some additional details. So, I generated this 100 different images, and I combine them with the noise, and I obtain this this blurry image, which also gives me some information about the angle that I look at it from, and I basically convert that into a gradient, and I will most probably come to that later on. So side by side, I will open up the paper and the code. So inside the stable DreamFusion, we have a train loader in the code. Why is there a train loader? That's the other point that I would like to talk about. Yep, so let's search for train loader. Yep. So here inside the main pie of this stable DreamFusion GitHub repository, we have a train loader, which takes in a nerf dataset, right? So, why is there a train loader that takes in the nerf? That was like one of my questions that I had in mind, and the answer to that is that because I'm not learning stable diffusion model, I'm trying to learn the nerf. The train loader is used to learn the outputs of these random poses, which I take from the nerf dataset. So that's an important point. Now let's move on to the explanation of this blue box again. You can think of this as a black box, essentially. You give it the prompt, it generates a denoised and structured image. This has to be consistent with the initial viewing angle. Later, this initial version gets merged with the noisy version. So why does it get merged? Because a neural net is an estimator, and the initial image is a high variance estimate. So the image that gets created after the merge is a low variance image. It is a gradient, so you can back propagate the weights of the MLP. So this is why I'm just combining like this noisy input to the output to this is high variance, this is low variance, and that's why I'm sort of merging this that's why I'm like merging this with the noisy version. So we looked at the render from 100 different angles. We created 100 different gradients, right, through these steps, and reaching here, we have created 100 different gradients. And we're using, and we're training the model using these 100 different gradients. And this is just our first epoch of training for the learning of the nerf MLP. And we repeat this step 100 times or 1,000 times, and this creates a 100 or 1,000 loop or epoch training session. Okay, so I've explained what an epoch looks like and what this whole training process looks like. So let's go back to MainPy inside the stable DreamFusion. And, I've obviously got, some parts from stable DreamFusion repository. My code, which is SD and Fusion SDS example, are, mostly borrowed from stable DreamFusion. So let's go to line 200 here inside the main. Yep. So yes, here. So we do not have to necessarily use stable diffusion. We can also use clip. I can basically use any text image model, but stable diffusion and clip are already implemented here. So we feed guidance to the trainer, right? So on line 329, let's go there. Yes. So you see here we're feeding guidance into our trainer. So this means that this 2D text to image model, this 2D text gets fed into this 2D text to image model, and later on, this trainer gets fed into this train loader, and that's where this basically that input goes through this nerf folder, all the most of the codes inside this nerf folder. So so we have a trainer here, and this utils is the utils here, and basically my the guidance once goes through there, it comes to here inside the nerf folder, and inside here it enters the train function, which is on line 718. Sorry, this is the train step. I'm looking for def train, and train function makes a call to train one epoch function, which is on line 929. Yes, it's here. And that makes a call to train step function, which is on line 368. And the important part of this training is inside this train step function. This important part is that on inside the train step function, train loader gives the parameters of the poses, which is on a line which says outputs equals. Let me find that line really quickly. There it is. So here what happens is this generates the 2D images of the poses that are being fed into train step, and I have this pred RGB, pred depth, pred mask, and this pred RGB here, and this is the image inside the output, and it gets it gets reshaped, right, which is not important. After the pred RGB gets passed from the diffusion model, it returns loss. It returns the loss here. Now, I think I was able to fully explain what happened within one epoch. I was able to explain, the input and, how I traced the code, how the code, and how the parameters get updated and how we generate the 2D shape, how we optimize it, and how we calculate some loss. So this is, I think, a good description of, what happened throughout the pipeline here. Let's move on to RealFusion. So RealFusion is really similar to DreamFusion, right? So the only difference is that it also takes in an additional 2D images input. It reconstructs based on 2D input. You also give the prompt because they have observed that if the diffusion model does not get conditioned based on text input, the generation process becomes harder. And the reason why they're close to, they are in close relationship with the DreamFusion paper is that they use here the SDS loss, which is also used in DreamFusion. They also use additional losses like normals and image and mask losses. But those are not that important. I mean, they're important. However, that's how DreamFusion paper relates to the RealFusion paper. Now, this is the end of this video. Thanks a lot for listening to me.